So good morning dear cadets. So today I have completed the monosaccharides. What are the monosaccharides? Which are the ultimate hydrolysis product of carbohydrate. Okay. Yesterday I taught you the cyclic structure of glucose and fructose, and we came to know that actually glucose is two types, alpha D glucose and beta D glucose. Okay. Then I taught you Haworth projection formula also, isn't it? In Haworth projection formula, how to represent the groups which are present in the right hand side of the open chain structure of glucose and which are present in the left hand side. So remember, in open chain structure of glucose, whosoever is, or in cyclic structure of glucose, whosoever is present in left hand side, in Haworth projection formula they will be down, okay, and the groups which are present in left hand side, they will be at top, at respective carbon atom. Once again listen, in cyclic structure of glucose or fructose, the groups which are present in right hand side, they will be down in Haworth projection formula, and those who are in left hand side, they will be at top at respective carbon atom. You should remember that one only. Then very easily you can form the Haworth projection formula for the glucose, that is also known as glucopyranose structure. Okay, and for the fructose it is known as fructofuranose structure. Fructofuranose structure, because of their analogy with furanose, or for glucose because of its analogy with pyran. Okay, so this is over now. Now today I am going to teach you disaccharides. So what are the disaccharides? Are the part of oligosaccharides. So as its name itself suggests, disaccharides, they produce two monosaccharide unit on hydrolysis. So the carbohydrate which yields two monosaccharide units on hydrolysis, they are known as disaccharides. Okay, and both monosaccharide unit in respective disaccharides, they held together by oxide linkage, that is known as glycosidic linkage. So what is the glycosidic linkage? Glycosidic linkage is means one type of oxide linkage by which or through which two monosaccharide units are held together. Okay, two monosaccharides units are held together through divalent oxygen or oxide linkage, that is known as glycosidic linkage. So what are the examples of disaccharide? The examples of disaccharides are sucrose, maltose and lactose. Okay, sucrose, maltose, lactose. What is their molecular formula? All three have got same molecular formula, but monosaccharide units are different. Like glucose and fructose, molecular formula is same, but you might have seen the functional group is different. In glucose, aldehydic functional group. In fructose, ketonic functional group. Similarly here, for sucrose, maltose, lactose, they are disaccharides. Their monosaccharide units are different. Okay, even though molecular formula is same. Okay, like sucrose. Now, sucrose will have two monosaccharide unit. One is glucose, other is fructose. But you will tell, sir, something else also you have written. Now, try to understand, in glucose, how many glucose is there? Two anomers are there. Alpha D glucose, beta D glucose. So, in sucrose, one monosaccharide unit is alpha D glucose. So, specific name of anomer should also be included, because earlier you were not familiar with the anomers. Now, you are familiar with the anomers. So, what are the anomers? Anomers are the special kind of optical isomers which differ in terms of configuration at carbon number first. Okay, but they are not enantiomer. Enantiomers, they form mirror image of each other, only they do not superimpose on it. Here what is there? Anomers, they do not form mirror image. So there is no question of overlapping it. Okay, so remember, they are a special kind of optical isomers. They differ in terms of configuration at carbon number first only. Rest all part would be similar. Okay. So in sucrose, one monosaccharide unit is alpha D glucose, and the next monosaccharide unit is beta D glucose, beta D fructose. Okay. Already I wrote here. What about maltose? Maltose is a simple disaccharide. It is made up of two common or same monosaccharide unit, that is alpha D glucose and alpha D glucose. Okay. So the monosaccharide units of maltose is alpha D glucose plus alpha D glucose. Of course, two monosaccharide units are there, but both are same here. Okay. What about lactose? Lactose is milk sugar. What is this one? Milk sugar. This is made up of two different monosaccharide unit. Okay. One is beta D glucose, other is beta D galactose. Galactose. Okay. Are you getting my point or not? So one conclusion we can draw here. What is that conclusion? In disaccharide, monosaccharides unit may be same, may not be same, may be different. Like in maltose, monosaccharide units are same, but in sucrose and lactose, monosaccharide units are different. Okay. We can say or not. Okay. Definitely polysaccharide will also be made up of monosaccharide units, but they will have many more monosaccharide units. In disaccharide, only two. Okay. In polysaccharides, many monosaccharide units. So first we will discuss disaccharides, and afterwards we will discuss polysaccharide. Okay. So just see, how can we say that sucrose is made up of alpha D glucose and beta D fructose, or how can we say that maltose is made up of alpha D glucose and alpha D glucose, lactose is made up of beta D glucose and beta D galactose. Now hydrolysis product will justify this one. Sucrose is known as cane sugar. Okay, because it is obtained from cane sugar. This can be obtained from beet also. Okay, that is why it is either known as cane sugar or beet sugar. Are you getting my point or not? Sucrose can be obtained from cane sugar juice and from beet. That is why it is known as cane sugar or beet sugar. Okay, now write down the molecular formula of sucrose. Sucrose is C12H22O11, subjected for hydrolysis, acidic hydrolysis. What is the name of enzyme? Invertase enzyme. Then you will get C6H12O6 plus C6H12O6. Okay, one is glucose, other is fructose. Now which glucose? This is alpha D glucose. Alpha D positive glucose. What about this one? This is beta D negative. So here negative D, I already told you, D the glyceraldehyde series, and positive and negative sign that indicate their optical rotation. Okay, so you know this one. Just see, there is one fact about the hydrolysis of sucrose. What is that fact? Just see here. The specific rotation of alpha D, this is alpha D, I have written here. This is the method of representing the specific rotation, optical specific rotation. Okay, optical specific rotation. So for sucrose, it is plus 66.5. Plus 66.5. Okay, this is optical rotation of sucrose. Means plus sign is here, it means sucrose is dextrorotatory. Okay, subjected for hydrolysis. Then here glucose and fructose is formed. Glucose specific rotation is plus 52.5, fructose specific rotation is minus 92.4. Minus 92.4. Okay, means out of glucose and fructose, glucose is dextrorotatory and this one is laborotatory, fructose. Correct or not? Now try to understand. There is one word, inversion of cane sugar. What is the meaning of inversion of cane sugar? And what do you mean by invert sugar? Those two terms should be explained. Even though in chemical kinetics chapter I have explained this one. Actually, the sucrose is dextrorotatory, but the resulting mixture which is obtained after the hydrolysis, that is laborotatory. So just see, the property in terms of optical rotation is completely inverted. it reversed. Started with dextrorotatory, but here we are getting the laborotatory mixture. Why laborotatory mixture? Just see. Fructose is minus 92.4 and glucose is plus 52.5. So now if you subtract this one, then you will get minus 39.9. Okay, means still, means of course this is minus, this is plus, so subtract it. So overall difference between dextrorotatory and laborotatory is there. What is that one? That difference is minus 39.9, means still minus, means laborotation is greater than dextrorotation. Okay, so this overall mixture is now laborotatory. I hope that you are getting my point. What is there? Glucose is dextrorotatory, but fructose is laborotatory, and fructose laborotation is minus 92.4. So even if you will subtract this one, still laborotation is greater than this one by minus 39.9. So this entire reaction mixture, this is now laborotatory. So this process is known as inversion of cane sugar. Means cane sugar was dextrorotatory, but upon hydrolysis whatever product is formed, that is now laborotatory. So this process is known as inversion of cane sugar, and the resulting mixture means mixture of glucose and fructose, that is known as invert sugar. So sucrose is dextrorotatory, but on hydrolysis product mixture glucose and fructose is laborotatory. Overall rotation is laborotatory. Overall rotation. What is the meaning of overall rotation? Overall rotation is difference of the rotation of glucose and fructose, that I wrote here, minus 39.9. So overall rotation is still laborotatory only. So this process is called inversion of cane sugar, means from dextrorotation to laborotation. So this process name is inversion of cane sugar, and product formed on hydrolysis is called invert sugar, glucose and plus fructose mixture. Okay. So actually this process is given in NCERT book, I told, but what is our basic topic? Our basic topic is I have to explain the glycosidic linkage which is present in sucrose, maltose and lactose. Okay, so one thing is sure here, that upon hydrolysis sucrose is producing alpha D positive glucose and beta D negative fructose. So those should be explained. Okay, how they are forming the glycosidic linkage. So now space is not there, I will rub that one and will make. Okay, see the glycosidic linkage in sucrose. Just in sucrose, what are the two monosaccharides unit? Alpha D glucose. So just see, a lot of confusion is also there in NCERT book, but you, whatever instruction I am giving, if you will follow, you will not confuse. Okay, just see, in NCERT book this is explained wrong. Okay, so please, this sucrose is there, this is the page number 409. 409. This structure is wrong, please just see. Okay, especially the structure of beta D fructose is wrong. Okay, the here CH2OH they have written top, it should be down, which I made, that is correct. Okay, so please take care. Now almost every year whenever I am teaching 12th class, I am explaining this one, try to understand. This is alpha D glucose. So first you make the open chain, means cyclic structure of alpha D glucose. So just see, alpha means what? At carbon number first of glucose, OH should be in right hand side. Okay, it is there. Just see, make the cyclic structure. On the basis of this one, you make the pyranose structure or Haworth projection formula. So whosoever is right hand side, they would be down. Like this is carbon number 1, 2, 3, 4, 5, 6. Okay, so just see, 1 carbon number, this is 1. OH is right hand side, I put down. H is left hand side, up. Second carbon, OH down, H up. Like that you make. This is Haworth projection formula for the glucose, or what you can say, this is glucopyranose structure. Glucopyranose structure. Same is the case. What is the next monosaccharide unit in sucrose? That is beta defractose. Okay, in beta of fructose. What is the meaning of beta defractose? See, in glucose, number 1 carbon atom is anomeric carbon atom, but in fructose, number 2 carbon atom is anomeric carbon atom. Okay, everything is happening at carbon number 2 because ketonic group is present at carbon number 2. So, if beta means OH in carbon number 2 should be left hand side. It is there, just see. And in right hand side, CH2OH group will be there. Okay, I hope that you understood this one. Just you remember this one, you will not commit mistake. And now on the basis of this one cyclic structure, you make furanose structure, furan structure of fructose, furan like structure of fructose. This is furanose structure of fructose. Just see, this is there, very easily you can make. Same rule, those who are at left, sorry, those who are at right, they will be down. Just see, carbon number 2, 3, 4, this is 5, this is 6, of course this is carbon number 1. So at carbon number 2, which are in right hand side, they would be down. Just see, 2 carbon, this is down. 3 carbon atom, H is in left hand side, so it would be down, OH would be upside. Okay, like that. It is made or not? Just over. Now just you remove 1 molecules of water. How you will remove the 1 molecules of water? In 1 carbon atom of glucose, OH group is there, and at 2 carbon atom of this one, OH group is there. So OH of 1 and H of another unit. So what would be there? Just see, minus H2O, minus H2O. Now just see. Now these monosaccharide units, just a minute, just held them together with the help of glycosidic linkage. First you make this monosaccharide unit, this one, this and this. Okay, here O is there, here C, here H. Now what would be there? Here O. I am talking of that O. Now they will be held together, CO. Now here second carbon atom, everything would be same, OH. Now here what would be there? This is third carbon atom. Here what is there? OH, and here H. Here C, here H. Here what is there? OH. Here C, here what is there? CH2OH, and here what is there? H. Correct or not? 1 monosaccharide unit is ready. Now make another one also. This furan structure. Okay, now here O is there, here C, H, here what is there? CH2OH, and here what is there? Just see, at this point, this O. Now carbon is there below this one, CH2OH, and here 3 number carbon atom, OH, and here H, here C, here H, here OH. Okay, now just see, these 2 units are held together by this divalent oxygen. This is only glycosidic linkage. Glycosidic linkage. Glycosidic linkage. Now just see, we can write this glycosidic linkage like that also. We can write this one, alpha beta glycosidic linkage. Why alpha beta? Because alpha of glucose, alpha anomer of glucose, and beta anomer of fructose is taking part. Okay, we can say or not? So alpha beta glycosidic linkage. One more thing we can tell. What is that one? The position of carbon atom. This is known as C1 and C2 glycosidic linkage. Glycosidic linkage. Why it is known as C1-C2 glycosidic linkage? Because C1 of glucose and C2 of fructose is involved in this glycosidic linkage. C1 and C2 glycosidic linkage. This is also known as alpha beta glycosidic linkage. Yes? Is there any problem? Yes. So as you wish, glycosidic linkage, alpha beta glycosidic linkage, or C1-C2 glycosidic linkage. So C1 1 number carbon atom of glucose, C2 2 number carbon atom of fructose, beta defractose. Over. So this is the glycosidic linkage present in the sucrose. Same way I have to explain in case of maltose. Same way I have to explain in case of lactose also. So what is the important thing here? You should remember here monosaccharide units and what kind of anomer is present in that monosaccharide unit. Like in sucrose, alpha D glucose and beta defractose. Now in maltose, alpha D glucose and alpha D glucose. Now in case of lactose, beta D glucose and beta D galactose. If you remember this one, you will never commit mistake, and with position you will remember. Okay, just see. Now glycosidic linkage in maltose. So just write down here glycosidic linkage in maltose. Okay, just see. First hydrolysis of maltose. Here plus write, plus H2O. The hydrolysis of sucrose, maltose and lactose takes place in presence of acid only. In which enzyme? Maltase. In case of sucrose, invertase. In case of maltose, maltase. In case of lactose, lactase. So now here what is the hydrolysis product? Glucose. This is also glucose. Alpha D positive glucose. This is also alpha D positive glucose. Okay, no problem at all. Alpha D positive glucose, alpha D positive glucose, both. Okay, so this is the alpha means OH at carbon number 1, it should be right hand side. Okay, in alpha form, and in beta form it should be left hand side. So this is alpha D glucose cyclic structure. Okay, cyclic structure. On the basis of this one, we have to make the Haworth projection or glucopyranose structure. So this is glucopyranose of alpha D glucose. Now same, two are there same. So here I wrote alpha D glucose. This is also glucopyranose structure or Haworth projection formula. Remember here C1-C4 glycosidic linkage is there, or alpha glycosidic linkage is there. So just see here. Now this is 1, 2, 3, this is 4, this is 5, this is 6. So the OH of this one, just see, H of this one and OH of this one minus H2O. Remove. This is condensation. What is this one? Condensation between two monosaccharide unit. In case of sucrose also, what was that one? Condensation between two monosaccharide unit. Their monosaccharide units were different. One was alpha D glucose, other was beta defractose. Okay, here both monosaccharide units are similar. Minus H2O. So now minus H2O. Now I will not make again. Just what I will do, just see. This is H2O between this one and this one oxygen atom. So this oxygen atom is holding both monosaccharide, this one and this one together. So this is only glycosidic linkage. What is this one? Glycosidic linkage between two monosaccharide unit in maltose, and both monosaccharide units are alpha D glucose. This can be known as alpha glycosidic linkage. This can also be known as C1 and C4 glycosidic linkage. Okay, No problem at all. Why C1, C4? Because one glucose, alpha D glucose, C1 carbon atom, and here what is there? C2 carbon atom is involved in the formation of glycosidic linkage. So as you wish, very easily you can remember this one. Alpha, why only one type? Alpha, beta? Because one unit is alpha, other is beta. Here both unit is alpha. So now you can say, you will tell sir, alpha and alpha dash. That is understood the moment you write one alpha, it is understood that both unit are alpha only, isn't it? So no need to write alpha and alpha dash. Even if you want to write alpha and alpha dash, so that is means that won't be wrong. Okay, you can write. So this is alpha glycosidic linkage. Over. Now what about glycosidic linkage in lactose? I have to explain. Okay, now see the glycosidic linkage in lactose. Lactose is known as milk sugar. What is this one? Milk sugar. Okay. Now if you subject it hydrolysis of lactose, just see, this is the molecular formula of lactose, acidic hydrolysis only in presence of lactase enzyme. So you will get C6H12O6, C6H12O6, but one is galactose and another one is beta D glucose and another one is beta D galactose. Which galactose? Beta D. Beta means what is there? At carbon number first, OH would be in left hand side. Okay, there is a two difference. Basically one difference between glucose and galactose. If you see the open chain structure of glucose, in glucose at carbon number third, OH is left hand side and H is in right hand side. Rest all places OH is in right hand side. Now just see. But in galactose, in addition to the third, fourth one OH is also left hand side. Just see. 1, 2, 3, 4, 5, 6 carbon atom. Okay, correct? Now just try to understand. Pay attention here. Okay. In glucose at third one, OH is this side, H is this side. Okay. In galactose, same configuration would be at carbon number 4 also. So in glucose only at carbon number 3, OH is in left hand side and H is in right hand side. In galactose at 4 number carbon atom also, just like 3 carbon atom configuration would be there. Rest everything is same, and now its cyclic structure is like that. This is cyclic structure. Rest everything is same. So this is the first difference between glucose and fructose. And only one difference. Second difference is not there. Now it's beta form. So beta form, what should be there? Now OH should be in left hand side. Just see, at carbon number first it is there. Now its Haworth projection formula of galactose is this one. This is beta D galactose. Okay, just see, at carbon number 1, whosoever is in right hand side, they would be down. So H is down, OH is up. At 2 carbon atom, OH is down, H is up. In 3 carbon atom, OH is in left hand side, so up, H is in right hand side, so down. Like that you arrange. So 1, 2, 3, this is 4, this is 5, and this is 6 carbon atom. Okay, this is beta D galactose. Beta D galactose. Now just see, this is glucose. This is, what is the second monosaccharide unit present in the lactose? Beta D glucose. So beta means OH should be left hand side at carbon number first. Rest everything is same only. This is cyclic structure of glucose, and this one is the Haworth projection formula of beta D glucose. So now just see, H of this one and OH of this one should be removed in the form of condensation only, H2O. So when this is removed, what is there? Just see. Now I will not make this side. Here only I will make the glycosidic linkage. Glycosidic linkage. So just see here. The glycosidic linkage is C, O and this one. Okay. This is glycosidic linkage. No problem. Just see, you can make this one. This is glycosidic linkage. So what kind of linkage this one? This is C1C4 glycosidic linkage. Glycosidic linkage. Okay, we can tell this one beta glycosidic linkage. Beta glycosidic linkage. Beta glycosidic linkage. Beta glycosidic linkage. No problem at all. So C1C4 glycosidic linkage, beta glycosidic linkage. We can say this one. Just you can say at C1 and here glucose fourth one unit, galactose first one carbon atom, and glucose fourth carbon atom. Rest everything is same only. No problem at all. Over. So now just see. Once again I am summarizing. In sucrose, what kind of glycosidic linkage? Alpha beta glycosidic linkage. C1C2 glycosidic linkage. In maltose, C1C4 glycosidic linkage, or that can be known as alpha glycosidic linkage. In lactose, what is there? C1C4 glycosidic linkage or beta glycosidic linkage is there. Now just see this. So this divalent oxygen, this is holding two monosaccharide units together in lactose. Over. So in this way the disaccharide glycosidic linkage is over. 3 examples are given and all the 3 examples I have covered. Okay, beta D galactose, beta D glucose. Okay. There is a one concept, that is reducing sugar and non-reducing sugar. Okay, just see, we'll cover that one also, reducing and non-reducing also. Okay, dear cadets, there is one more concept, that is reducing sugar and non-reducing sugar. Okay, so just see, in all the monosaccharides and disaccharides, what you have got? 2 types of structure you have got, open chain structure and cyclic structure. Correct or not? Just see. So very simple thing is there, saccharides which, just first see the example. Actually monosaccharides and some of disaccharides, they are reducing sugar. Glucose, fructose, that is monosaccharide. Maltose and lactose, they are disaccharides. Okay, so these are reducing sugar. Okay, so how can we say, or what are the characteristics that they have got to have character like reducing character? Okay, that we have to explain. Are you getting my point or not? What are the characteristics feature they have got, that is why they have been classified as a reducing sugar. Okay, now non-reducing sugar, only one example is there, that is sucrose. So what are the characteristics of sucrose, because of which it is classified as non-reducing sugar? Just see. The first one is very simple, saccharides. I am using word saccharides. Under this one monosaccharide will also come, disaccharide will also come. Okay, so saccharides which can reduce failing solution and tolerance reagent. Failing solutions and tolerance reagent, they are called reducing sugar. Saccharides which cannot reduce failing solution and tolerance reagent, they are called non-reducing sugar. Okay, that is the first characteristics. Okay, and a simple one. Second one is saccharides which have free CHO or ketonic group with OH group at adjacent carbon atom in their open chain structure, they are called reducing sugar, or they will exhibit the property of reducing sugar. Are you getting my point or not? They should have free, just see, suppose glucose I am writing in CHO, and here what is there? CHOH, and here what is there? OH and H. Correct or not? Like that you can write 6 carbon atom. So just see, here free CHO group is there, and this is the adjacent carbon atom, this one, and this adjacent carbon atom is having OH also. Same is the case with the ketonic group. This is CH2OH, here what is there? C double bond O, this is H, and this is OH. Now try to understand here. This is ketonic group. This is adjacent carbon atom. Here OH group is there. Correct or not? So just see, saccharides which have free CHO are free ketonic group with OH group at adjacent carbon atom. With OH group at adjacent carbon atom in open chain structure. In open chain structure. So they are reducing. Okay. Now just see, in glucose, fructose, not only this one. If you will form the maltose structure and lactose structure, so what in maltose, what kind of glycosidic linkage is there? 1,4 glycosidic linkage. 1,4 alpha glycosidic linkage is there. 1,4. So just see, one unit, one glucose, one carbon atom, and another glucose, 4 carbon atom is involved. And whose 4th number carbon atom is involved, its one carbon atom is free. So the glucose is there, so CHO group is free or not in maltose. Same is the case with lactose. In lactose, what kind of glycosidic linkage is there? In galactose also 1,4 beta glycosidic linkage is there, or 1,4. So here also one carbon atom 1, another carbon atom 4, and whose 4th is involved, there one is free. So at one number only CHO group would be there. So means what is there? What is there? They should have free CHO or free ketonic group along with OH group at adjacent carbon atom in open chain structure. I am talking open chain structure. Okay, no problem at all. So I hope that you have got. Now you can see the structure of maltose and lactose. You can't have any problem in glucose and fructose, but you may have problem in case of maltose and lactose. So you can see there one carbon atom at least will have free CHO group. Free CHO group in open chain structure. Okay, over this one. Now another characteristics. Now in cyclic structure. In cyclic structure, they should form hemi-acetal form or hemi-ketal form. Just see. Try to understand when you are forming the cyclic structure of glucose. Just see. Now in the short I will make here only cyclic structure of glucose. Just see the cyclic structure of glucose. How you are forming cyclic structure of glucose and fructose. So just see. This is C. Here OH will be there. Here H. Here what is there? H and OH. This is C. This is OH and this is H. Like that you can make. And now this oxygen atom from 5th number carbon atom. Okay. 1, 2, 3. And here also. Can I delete this one? Because this characteristics I have explained. Now so we can delete. Make this one 3. This is 4th number H and OH. Here C, here H, 1, 2, 3, 4, 5. This is oxygen atom. Already I wrote oxygen atom here only. Okay. And this is CH2OH. Okay. This form is known as hemi-acetal form. So this is hemi-acetal. Just see. C, OH, H. And I am talking of this oxygen. So here this is hemi-acetal form. Okay. Just you can check. So in cyclic structure means those saccharides which is existing as a hemi-acetal form or hemi-ketal form in their cyclic structure, they will be called reducing sugar. So just try to understand. Glucose, fructose, they are having this form. Not only this one, in maltose what is there? In maltose glucose are there. So if glucose is reducing sugar, so maltose will also be reducing sugar. Now you will tell, sir, in sucrose, glucose and fructose both are there, but that is non-reducing sugar, because in sucrose what is there? 1,2 glycosidic linkage is there. So 1 of glucose unit and 2 of fructose unit, correct? 2 of fructose unit, because fructose is having ketonic group at 2 number carbon atom. So 1, 2 where free CHO and where free ketonic group should have been. So their free CHO and free CO group is involved in the glycosidic linkage. So their free CHO group and free CO group is not there, because their glycosidic linkage is C1, C2. So C1 of glucose and C2 of fructose unit. So where free CHO group is there, those who have got 1,4-glycosidic linkage, they will have free CHO group or free ketonic group. They are called reducing sugar. So just see. Now this is hemiacetal form. So glucose is found in the hemiacetal form. Fructose also will have the hemiacetal form. Just see. Fructose, hemiketal form. Fructose structure you can make like that. Cyclic structure. How you will make? Just see. This is the first carbon atom CH2OH, and here what is there? C double bond O, H. This is third one OH, and here H, here C, H and OH. Here what is there? CH. Now shift one H here. So this double bond and H. This is cyclic structure. 1, 2, 3, 4, 5, and this is 6 number CH2OH. So what is the hemiketal form? Just see. CH, OH, and CH2OH. And this oxygen is glycosidic oxygen. Okay, so this is hemiketal form. So those who have got hemiacetal and hemiketal form, means those who are existing in hemiacetal and hemiketal form, they will have reducing character. Now saccharides which do not exist in hemiacetal or hemiketal form in their cyclic structure, they are called non-reducing sugar. The best example is sucrose. Sucrose hemiacetal hemiketal form won't be there, because in the sucrose monosaccharide units are glucose. Which glucose? Alpha D glucose and beta D fructose. So in alpha D glucose, 1 number carbon atom is involved in the glycosidic linkage. In fructose, C2 carbon atom is involved. So at 2 number of fructose, ketonic group is there. At 1 number of glucose, aldehyde group is there. Both are involved in the glycosidic linkage. That is why what is there? Their hemiacetal and hemiketal form is not there. Okay, especially it won't have hemiacetal, neither have hemiacetal nor have hemiketal form. That is why this is sucrose. The best one is this definition. Okay, now it will not reduce saccharides which do not reduce failing solution and tolerance reagent. There is one more ambiguity here. Generally when I taught you failing solution and tolerance reagent, that what I told you, that only aldehydes reduce tolerance reagent and failing solution. Ketone does not. Correct or not? So just see, fructose is having ketonic group. So fructose should not have reduced the tolerance reagent and failing solution. Am I correct or not? I only told you now when I was teaching you aldehydes and ketone, at that time what I told you, only aldehydes can reduce the tolerance reagent or failing solution, or else also we can say tolerance reagent and failing solution can oxidize only to aldehyde, but they can't oxidize the ketone. Okay, that I told you. But fructose is having ketonic group, nevertheless it is reducing the tolerance reagent and failing solution. That is why it is under the category of reducing sugar. Why? That is the question. Try to understand here. Whenever fructose is reacting with, or when fructose treated with dilute alkali, so it undergoes isomerization. And because of this isomerization, it gets converted into glucose. Just see, check that one also. It is very simple thing. Just see, this is fructose CH2OH. This is C double bond O, CH and OH. This is CH and OH at 3 number carbon atom, like that. Now CH and OH, 1, 2, 3, 4, 5, and this is 6. Okay, this is fructose. When you are treating this one with dilute alkali, okay, then what would be there? Just see, isomerization would be there. Its 1H will come here. So it would have now COH form, here double bond, here CHOH form. Rest everything would be like that. OH and here H, here C, here H, here OH, here C, here H, here OH, and here what is there? CH2OH. Correct or not? Just see. Now this is ene-ol form. Ene for double bond and ol for this one. further, just see, further isomerization would be there. You do one thing, shift one H here. Now in this case one H has come here, that is why this form is there. Further one H you shift here. So now here what would be there? CH and OH. Now here at the end what is there? CHO. Rest every places OH and H. Here also CH and OH. Here C, here H, here OH, here CH2 and OH. So just see, this is glucose now. This is glucose and this is fructose. This is fructose and this is enol, or you just say enol form. What is this one? Enol form. Okay. Now when it is happening, when you are treating fructose with dilute alkali. So what is there? Just what is my question? Do you understand or not? Fructose is having ketonic group. Nevertheless, it is reducing tolerance reagent and failing solution. Correct or not? That is why it is called reducing sugar. So why it is called reducing sugar despite having ketonic group? Because when actually fructose isomerize into glucose in this way. So in the dilute alkaline solution of fructose, some amount of or some percentage of glucose will also be there. And you know in the glucose aldehydic group is there. That is why fructose reduces the tolerance reagent and failing solution. Correct or not? Because fructose some isomeric form is this one, glucose. Okay, this is the reason. In this way, now I have completed the disaccharide. Actually that has not been discussed, but since I wrote there fructose, so now somebody may raise question that in fructose what is there? Ketonic group is there. Nevertheless, it is reducing tolerance reagent and failing solution. That is why I have explained. I hope that you understood my point. Okay, thank you. Now we'll teach tomorrow polysaccharides. There also will explain the glycosidic linkage. Thank you.